Decimal, octal, hexadecimal, ternary, sexagesimal, quaternary. There are so many number systems out there. Then what makes binary the choice to store data in computers? Be it the hard disk, the RAM, or the processor? Why not use decimal, which we are more familiar with? Let's find out what's so special about binary. In computers, each binary digit is represented by presence or absence of current in a component called cell. When the current is present, we say it's a binary 1, and when it's switched off, we say that's a binary 0. It is easy to represent two digits of binary by two states of current, that is on and off. Whereas if we use decimal, then there will be 10 digits and we must have 10 distinct states of current. One way to have 10 distinct states could be to use voltage of the cell as its value. We may take 0 volts to be digit 0, 1 volt to be digit 1, and so on. We can connect a voltmeter to a cell to get the voltage reading of that cell. This reading represents the decimal digit stored in that cell. In this way, we can connect a voltmeter to each cell and have 10 distinct states to represent the 10 decimal digits. But there is a problem with this approach. Computers store millions of digits. Since we should have a voltmeter for each digit we store, it becomes too expensive. It's not the only issue. There's one more problem. Current doesn't come in exact voltages like 0, 1, 2. Instead, it keeps fluctuating due to resistance caused by length of the wire, interference from nearby circuits, crosstalk, and many other reasons. These concepts belong to a branch of physics or engineering that deals with electricity and electronics. Let's have them for some other day. For the sake of time, let's switch back to computer science. Now these voltage fluctuations make it harder to assign a particular voltage to a particular binary digit. In fact, the binary digits stored in computers are not 0 volts and 1 volts. Instead, any voltage close to 0 volts is considered to be a binary 0, and any voltage close to 5 volts is considered to be a binary 1. Even if we adopt a similar solution for our 10 states of representing a decimal digit, still the voltmeters make this approach very expensive. Even if we come up with an approach that doesn't require any extra equipment, like we used voltmeters to identify 10 different states, still we would end up with other sort of disadvantages compared to using binary. Let me show you an example. Let's devise a strategy that uses the same logic of presence and absence of current, but lets us create 10 different states for 10 decimal digits. Let me show you how. This approach requires 10 cells to store a single decimal digit. It goes like this. If the first cell is on and the rest are off, it is a 0. If the second cell is on and the rest are off, it is a 1. If the third cell is on and the rest are off, it is a 2, and so the rest. Looks like we have devised a great way to store decimal digits without the use of any extra equipment like voltmeter or ampere meter or any such stuff. But now we have a new problem. We now require a huge number of cells to represent a decimal number using this method. Consider number 11. To represent 11 in decimal using our method, we require 10 cells to represent the first digit, which is a 1. Similarly, we require 10 more cells to represent the second digit, which is also a 1. So we require 20 cells to store 11 in this method. Instead, if we represent 11 in binary, it would be 1011. A single cell would suffice for each binary digit. The ones would just be denoted by mere presence of current, and the zeros would be denoted by the absence of it. So we require just 4 cells in total to store 11 in binary. If that doesn't seem a convincing difference, consider this 10-digit number. Using our method, it would take up 10 cells per digit, costing us 100 cells to represent the entire number. Instead, if we convert it to binary, it would be a 32-digit number and just take 1 cell per digit, costing us a few 32 cells. Now that's a huge difference. This advantage of binary makes it one of the most efficient systems to store data in computers. A binary digit is called a bit. A bit can be 0 or 1. 8 bits are said to be a byte. We can represent numbers ranging from 0 to 256 using a byte. 1024 bytes make a kilobyte. 1024 kilobytes make a megabyte. 1024 megabytes make a gigabyte. And such 1024 gigabytes make a terabyte. Personal computers generally have a hard disk of 1 terabyte, which is 10 to the power of 12 bytes. That equals 8 trillion bits. That is, your hard disk can store 8 trillion ones and zeros. Any user usually inputs numeric data from the keyboard mostly in decimal form, as that's what he is familiar with. But a computer will convert that decimal number to binary when storing. Even if the given input is text, a computer stores it in binary using a convention called the ASCII, short for American Standard Code for Information Interchange. In ASCII, each English alphabet is represented by a number. The ASCII table has both the uppercase letters and also the lowercase ones. It also has some commonly used symbols. Now let's input some text and see how the computer will interpret it. Let's input "Hey Jawad." First we type the uppercase H. Its ASCII value is 72. The computer will convert it to binary as 1001000 and stores it. Next we type the lowercase e. Its ASCII value is 101. The computer will convert it to binary as 1100101 and stores it. Similarly, it stores lowercase y. Even if we hit the space bar, the computer will store it as binary equivalent of 32. Similarly, it stores the uppercase j, lowercase a, w, a, and d. Even if we input a symbol like the exclamatory mark, the computer will store it as binary equivalent of 33. Even the arithmetic and logical operations that the ALU performs are done in binary. If we had used decimal instead of binary, then the ALU needs to memorize many rules. In decimal system, even a simple operation like addition uses so many rules as follows. Then we have the multiplication, where again kids are taught to memorize so many rules. The set of rules or instructions one must memorize in order to perform arithmetic operations in binary are far more less compared to what we memorize to perform arithmetic operations in decimal. This adds to our bucket of reasons to prefer binary for computers over decimal system, or for that matter, any other number system. But how does one add, subtract, multiply or divide binary numbers? And what do logical operations such as AND or XOR mean? That would be the topic for our next videos.
Hey there, hope you like the video. This video is part of series called Computer in a Nutshell. If you are new to computer science, then this is the only series you'll ever need to get started. Because this series will take you on a crazy ride, starting from what is a computer, to what's inside a computer, to how each part of computer works, leading all the way up to Introduction to Programming.
To get started on this series, you can head over to my channel and dial into Computer in a Nutshell playlist. Here, you can find all the videos from this series in chronological order. You can also find links to the videos from this series in the description of every video.
If you find this video informative, please share it forward. Subscribe to our channel for more such videos. Click here to watch the next video from this series. You can also check out our previous video from here.